Last time we talked about the spherical propagation factor and how it is e to the minus j k r over r for all the fields from a finite source like an antenna, and how that means that power from a source like that is proportional to 1 over r squared. That also means that if you have a source that radiates a certain amount of power, let's call it P rad, because that is what you call radiated power, and it is spreading out spherically because of the spherical propagation factor, on average, the power density over the surface of that sphere is going to be P rad divided by the surface area of the sphere, 4 pi r squared in watts per meter squared. So that's always going to be the average power density radiated by a source. The interesting thing about antennas is how is that power density concentrated in some areas as opposed to others? And we sort of touched on that when we said that the electric field from any finite size source that obeys these antenna rules in the far field, so I'm going to give it a little FF subscript there, can be broken down into two parts where we have some electric field vector that is a function of only angle, that gives you all the vector and angle information. It gives you vector direction, and it gives you angle dependence. And then you have this other term, e to the minus j k r over r, the spherical propagation factor. Now, most of the properties of antennas have to do with this first part with the angle dependence, because all antennas have a spherical propagation factor. We all know about it, so there's not a lot of new information there. We kind of ignore it most of the time. But we talk a lot about the radiation pattern. Now, that's a general term that is meant to describe this angle dependence, but it can be normalized in a variety of ways. So that's a general term that doesn't really have a specific definition. On the other hand, we have things like directivity and gain, which are more specific ways of normalizing this angle dependence. And we'll talk more about those later and how they're different from each other. I'm going to tell you a few other important antenna words to begin with, and then we'll sort of jump in to all of these different antenna metrics. A key word to know here is isotropic. And that means that it radiates equally in all directions. If you have some source that is an isotropic source, that means that its radiation power density is the same along every angle, so it's shaped like a sphere. The radiation pattern is a sphere. Antennas have polarization, but unlike plane waves, Usually the polarization vectors are related to theta or phi, because the propagation direction is along the radial direction. So since k is r-directed, you end up with electric fields that are perpendicular to k. So usually we're talking about things in terms of the theta and phi unit vectors rather than the Cartesian unit vectors like we did for plane waves. We also have radiation resistance. And more generally, impedance. And these are the resistance or impedance that we could replace the antenna with in a circuit and get the same terminal voltage and current. Now, a key thing here is that radiation resistance also has key things to say about power and efficiency, and we'll touch on that later.